Hello everyone, welcome back to this online class. Today we are going to look at numerical solution of ODEs, and we are going to look at the boundary value problems, and in particular we look at the shooting method. So we have this question. We are asked to use a shooting method to solve the boundary value problem given by d squared y over dx squared is equals to x plus y, subject to the boundary conditions that at x is equals to 0, y is equals to 1, and at x is equals to 1, y is equals to 0. With the step size h is equals to 0.25, we use Euler's method to solve the corresponding initial value problem and compute the values of y of 0.25, y of 0.5, and y of 0.75 correct to 6 decimal places. So, what is the idea behind shooting method? Is that for you to use this method to solve boundary value problems, you first of all need to convert your boundary value problem into a corresponding initial value problem. Once you have the initial value problem, then use those methods that we discussed previously of solving initial value problems. That is, you can use either Taylor series method, you can use Euler's method, or you can use modified Euler's method, or you can use Runge-Kutta method. Those are the various methods of solving initial value problems. So for this case, we have been told to use Euler's method. So let's see how to go about the problem. Now, that given equation, the ODE that we have been given is y double prime is equals to x plus y. I want to convert. Remember, our condition is that y of 0 is 1, and y of 1 is equals to 0. So, for you to convert it to a corresponding IVP, remember IVP, the conditions are defined at only one point. So, because this is a second order ODE, I will need two initial conditions. Already the first one is given, y of 0 is 1. You will let another initial condition to be y prime of 0. Let it be alpha, because we are converting this to an IVP. Remember, IVP, you need initial conditions. And when we talk of initial conditions, the conditions are defined at just one x value. You can decide that let us define them at x is equals to 0. So for this case, we will need two initial conditions because our ODE is a second order ODE. So we need two initial conditions in the value in the dependent variable y. So let's convert it now. This alpha here is an assumption, it's an approximation. Let me comment on it. The alpha is an approximation for the gradient. Approximation for the gradient. And our gradient is y prime at x naught. So we are approximating using alpha. So it means we will need to find the value of alpha, and I'll tell you how to find it. So now, for us to because now we are converting to the corresponding IVP, so it will be that the IVP is such that y double prime is equals to x plus y, subject to the initial conditions that y of 0 is equals to 1 and y prime of 0 is equals to alpha. Now this is an IVP. You must understand the difference between an IVP and a boundary value problem. When we talk of a boundary value problem, the boundary conditions, the conditions are defined at maybe two different x values. So for this case, this is a 2-point boundary value problem. You see here we are defining at x is equals to 0 and another one at x is equals to 1. Two different x values. That becomes a boundary value problem. So this is a 2-point boundary value problem. Now, for us to use Euler's method, because now this is an IVP, remember Euler's method that we know is defined when you have a first order ODE. But for this case, we have a second order ODE. So how do we convert from a second order to a first order? So you can reduce it to a first order ODE, reduce it to a first order or a system of first order ODEs. How do we do this? We are going to say let z be equal to y prime, so that when I differentiate both sides, I'll get z prime is equals to y double prime. And what is y double prime? That is x plus y. So I can write down this. You can just say, or the first equation is that y prime is equals to z, and y prime is just dy dx. So y prime is equals to z, and the other one is z prime is equals to x plus y. So we have reduced our second order ODE to a system of first order ODEs. And what are the initial conditions? The initial conditions for y is that y when x is 0 should be equal to 1. What about for z? Z when x is 0 is the same as y prime when x is 0, and we have it here. That is the same as alpha. So remember, take note that when I write y prime, the same as dy dx in this case, and when I write z prime, is the same as dz dx. So that this can be written as, when I evaluate at x is equals to xn, so you can write evaluate at the point at x is equals to xn to get, so we'll have y prime of xn is equals to, remember z is also a function of x, z of xn, y double prime, not y double prime, but z prime of xn is equals to xn plus y of xn, of which this you can as well write as, so this is the same as writing, is the same as writing that y, this is prime, n is equals to zn, and z prime n is equals to xn plus yn. So the question is, what is the Euler's method when you have a system of first order ODE? I want us to recall, when we have dy dx is equals to f of xy, then the corresponding Euler's method is that yn plus 1 is equals to yn plus h of f of xn yn. What if now we have a system? So we'll have for this one and also for this, each of them. So therefore, the Euler scheme for the corresponding system, Euler scheme for the given system, I'm talking about this system, that will give us yn plus 1 is equals to yn plus zn. Not zn, but this h times zn. H times zn. And this other one, this one for z prime will give us zn plus 1 is equals to zn plus h times xn plus yn. That's what we have. Or simply, you could approximate the derivatives in this and also this using the forward Euler scheme. You know y prime n is the same as yn plus 1 minus yn over h. That's what you want to have substituted here. And then here, and then you cross multiply. Also, when we write zn prime is the same as zn plus 1 minus zn. This is over h. This is forward Euler scheme. Forward Euler. So you are going to get these two iterative schemes. And what about the boundary conditions? Y of x naught is equals to 1. So our conditions are that y naught is equals to 1 and z naught is equals to alpha. Let me explain what I mean. Remember, this is how the problem looks like. We are starting from x0 and the step size h was 0.25. So the next is 0.25 followed by 0.5 followed by 0.75 and the last one is 1. When you look at the boundary value problem, the given problem, let me take you back. So this was our x naught and this is our xn. I don't know n, but depending on the step size h, which is 0.25, I will know the value of n. So when you come back to this diagram, you realize that this is x naught, x1, x2, x3, x4. What is the corresponding values of y? Y naught was 1 when x is 0, and when x is 1, the value was 0. So I don't know the value here, this one, and also this. Those are the ones I need to find. So this is y naught, y1, y2, y3, and this is y4. So that's why I was saying that when we write y of 0, 0 means when x is 0, so that's what we're calling y naught. That's what I've written here. And z of 0 means z at x naught, which you have said is alpha z naught. So now the task is, remember we have converted our problem, which was a boundary value problem, to an initial value problem. And we are assuming that the gradient is alpha. Let me illustrate this before I tell you the task. In shooting method, we have x naught is here, and let's say here we have xn. In this case, it is x4. We are going up to x4. Let's say this is the value of y naught, and the value of y4 is somewhere here, y4, which is the same as y of x4. That's what we have. So because we are assuming that y prime naught is alpha, what it means that we are assuming that let the gradient or the slope be equal to alpha. So you are going to be shooting. This is alpha. You are going to shoot because our target is y4. For that value of alpha, I want the value of alpha that will get us to y4. So that is the task. So we are shooting, and so this is called our target. Our target is that y4 should be equal to 0. And y4 is the same as y of x4. You could also choose another value of alpha. Let's call it alpha 1 as the gradient. If I start with that, let us shoot. You might find that you get a different value of y4. It won't get you to the same point. So this means this is y1 of x4, not y1. Of course, the first shot, we call it first shot. It is undershot, undershoot. You see, the value we are getting is not the same as that of y4. It is less than that of y4. What if somebody will have chosen the value here to be maybe alpha 2? The gradient, let it be alpha 2. Maybe something like this. Call it alpha 2. If you do the shooting again, you will realize that this will land us to maybe another point here. That point, I can call it y2 of x4. This is the second shot. Second shot. It is now an overshoot. Overshoot. So the question is, for what value of alpha will land us to the same point? That is the task that we need to find. So you can write this, that our task in this case is to find, so you can write here, that the task is to find alpha such that y of x4, which is equals to y of 1, will give us 0. Let me just write such that y4, y of x4, which is y4, should be able to give us 0 because it is the target. So then this means that this is a root finding problem. So let me explain this. This is target. Just you're shooting, aiming at the target. So therefore, it means this is a root finding problem. A root finding problem. And when we talk of root finding problem, there are various methods that you can use. You can use what we are calling the bisection method. You can use Newton-Raphson method, etc., to be able to find the value of alpha, especially when your equation is nonlinear. If it is linear, then there will be no problem. But if it is nonlinear, you will have to employ such methods. So having explained that one, let's now go back to our IVP. Let's solve this subject to these conditions. We start with the first iteration. Remember, we are iterating for n is equals to 0, 1, 2, etc. until we get to y4. We stop at y4 because once you get to the target, you stop there. So let's write the first iteration where n is equals to 0. You can write here, put n is equals to 0. So what does it mean? That I will have y1 is equals to y0 plus h z0. And do I know y1? Yes. So this is equals to, I don't know y1, but I know y0. Our y0 is 1. I know h to be equal to 0.25. Do I know z0? That is alpha. And so when you press this, you need to get your value of y1 as 1 over 4 alpha plus 1. 1 over 4 is 0.25. What about z1? For the same problem, let's work it out here. z1 will be equal to z0 plus h into x0 plus y0. And so our z0 is alpha, h is 0.25, our x0 was 0, and what about our y0? It is 1. So this should give us alpha plus 1 over 4. That's the first iteration. Remember, we are going all the way up to y4 because y4 is the target. Once you get to y4, we stop the iterations. Let's go to the next iteration. You put n is equals to 1. What will it give us? That will give us now y2 is equals to y1 plus h of z1. And this is equals to, we know y1 to be 1 over 4 alpha, that's our y1, plus, it was plus 1, remember, plus 1, then plus h, which is 0.25, times our z1, that is alpha plus 1 over 4. When you work out this, you need to get y2 is equals to 1 over 2 alpha plus 17 over 16. Proceed to find z2. So you can write here z2 is equals to z1 plus h of x1 plus y1. Our z1, we have found it as alpha plus 1 over 4. Our h is 0.25. x1 was 0.25. y1 is 1 over 4 alpha plus 1. That's what we have. Let's simplify. This should give us z2 is equals to 17 over 16 alpha plus 9 over 16. Proceed with the next iteration. That is when n is equals to 2. So you can write put n is equals to 2. So what are we going to get? We'll now find y3 is equals to y2 plus h of z2. And that is equals to our y2. We have just found it to be 1 over 2 alpha plus 17 over 16. Our h is 0.25. Z2 is 17 over 16 alpha plus 9 over 16. When you simplify this equation, you need to get y3 is equals to 49 over 64 alpha, 49 over 64 alpha plus 77 over 64, 77 over 64. Let's also find Z3. So here Z3 is equals to Z2 plus H into X2 plus Y2. Our Z2 is 17 over 16 alpha plus 9 over 16 plus our H is 0.25 into our X2. What was it? We can confirm. Our X2 is 0.5. So that's what I write here. 0.5 plus Y2, which is 1 over 2 alpha plus 17 over 16. If you simplify this, you need to get Z3 is equals to 19 over 16 alpha, 19 over 16 alpha plus 61 over 64. And finally, of course, the next one will get us to Y4. So you can write put n is equals to 3. Remember our target was Y4. So when n is equals to 3, we are going to get Y4 is equals to Y3 plus H Z3. And our Y3, we have it as 49 over 64 alpha plus 77 over 64. Our H is 0.25. And then our Z3, we have just found it as 19 over 16 alpha plus 61 over 64. And then if you simplify this one, you need to get Y4 is equals to 17 over 16 alpha over 16 alpha. This is added to 369 over 256. 369 over 256. So we stop there. You don't even need to find Z4 because once you've reached your target, our target was Y4 and we have found it in terms of alpha. So we stop there. That is the end of the iteration. So, and what was the target? That Y4 must be 0. So we can go back and comment here because we said the target is that the value of Y4 that we are finding, you check from the diagram, we need the value to be 0. So let's go back and work it out. So you write the target is, of course, the target solution is that Y4 must be equal to 0. But what is the value of Y4 that we have found in terms of alpha? It is this one. So this therefore means that, therefore, 17 over 16 alpha plus 369 over 256, this must give us 0. You see now it is a root finding problem. This is what I was calling a root finding problem because we need to find the value of alpha that satisfies this equation. So this is a root finding problem. Root finding problem. For this case, it is linear. It is easy to find the value of alpha. So you're going to get alpha is equals to, make alpha the subject, that should give you negative 369 over 272. Negative 369 over 272. So that's our value of alpha. So with this value of alpha, we are going to substitute it back, because you see our unknowns were y1, y2, and y3. And now go to the expression for y1. Y1 was 1 over 4 alpha plus 1, and you now know the value of alpha, so you replace it. Similarly, do that to y2 and y3, and that will give you the required solution. So you can write this. We are now substitute alpha into alpha into y1, y2, and y3. What are we going to get? Let's start with y1. Y1 is equals to 1 over 4 alpha plus 1. That will be 1 over 4, and our alpha is negative 369 over 272. This should be added to 1, and the result is equals to, when you do that, you need to get 0.660846. 0.660846. That is correct to 6 dp. Do the same to y2. Our y2 is 1 over 2 alpha plus 17 over 16. So 1 over 2 alpha plus 17 over 16, and so that is 1 over 2 into negative 369 over 272 plus 17 over 16. And that should give you the value as 0.384191. 384191. Finally, y3 is equals to 49 over 64 alpha over 64 alpha plus 77 over 64. That should give us 49 over 64 times negative 369 over 272 plus 77 over 64. Press that correct to 6 decimal places. That is 0.164465. 164,465. So what do we mean by y1? It was the value of y when x is 0.25. y2 is the value of y when x is 0.5. And finally, y3 is the value of y when x is 0.75. And so we have found the values. Those are the answers. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving numerical solution of boundary value problems. Bye-bye.